Hey everyone, welcome back to the Summer Pi series, and in this video we're going to learn how to generalize a neural network so that it could handle different data sizes and data types. So if you've noticed through the code, depending on the size of your image, you'll have to downsize it until you get a feature map of 4x4 in the convolutional neural network. The approach that we're going to use now can be applied to other networks as well, so just keep that in mind. So the problem with this is that we had 64 by 64 images, but let's say you wanted to use a higher resolution, maybe 512 by 512, then it's not really efficient to keep copying and pasting the sequence of layers. There's a smarter way to do all of this. So in standard deep learning models such as that you might find in other sources, you'll often find that they're working with image sizes of 64 by 64, 256 by 256 maybe 512 by 512, but it could increase. But if you keep it at these types of numbers, you'll notice that there's a similar property between all of them. They're all exponents of 2. Now recall when building the CNN, we would constantly cut the dimensions in half until we reached 4x4 feature maps. So how many times do we have to cut it in half? It's really just the exponent minus 2. So how can we generalize this? Consider the expression where 2 to some value x gives you the size y. Well, we need to solve for the exponent value x then. To do this, we just need to use the log function. You apply the log function to both sides, and it has this property where if there's an exponent, you could bring it down. We could isolate x and then solve for it. Now we just need to subtract this value by 2. And now we're going to learn how to code this. So to do this, we're going to start off with the typical process again, of course. And this one I'll just call CNN. Really, it's just a generalized CNN. And another input that we're going to take in is the image size. So then we need to change the name in the super function. And then we're ready to start. So then we'll say exponent equals the integer value of math.log of the image size divided by math.log of 2. So then what's happening here is, if you remember the expression, we're taking the log of the image size and divided it by 2, and that's how we isolated the exponent. And then we need to say integer value because it might be calculated as a float value, but we need the integer. We just need the solid number. So note that we're using a new library called math, so I'll actually have to say import math. And what I'll prefer to do instead is bring it up to where the rest of our imports are. So now what we have to do is we have to start our CNN. So we could start building it here. We're going to start it off with the first set of layers. So the convolutional layer, which brings the number of channels to the number of feature maps. We'll use the 421 for the kernel, stride, and padding. Again, we'll use batch normalization. Normalizing the number of feature maps, and then we'll have our activation function. So the reason we have to start it off like this is because we're going from number of channels to number of feature maps, and we can't put that in a loop, which you'll see in what we do next. So what we're going to do now is create a loop to build the rest of the network. And what we're going to say is for I in range exponent. So remember, how many times are we cutting it in half? Well, it's the number of exponents minus 2. But then we started it off already with its first layer, so we have to subtract another 1 here. But let's just combine that to say minus 3. And every time you go through this loop, you're just adding this sequence of layers again. So we're going to say dot CNN plus equals, we're going to add this series of layers to the network. Now what we do have to change here is now we're going from NFM to NFM times 2. So remember how every time we went to the next convolutional layer, we doubled the size of the feature maps. So the easiest way to express this is to just say NFM times 2 to the ith power. So this just means exponent, so this is 2 to the ith. And then we'll say NFM times 2 to the I plus 1 power. This might be a little confusing for some people, but let's just go through the loop so we can make some sense of it. So on the first iteration of this loop, I will equal 0. So then this will say NFM times 2 to the 0th power, which is 1. So that's NFM times 1. And then this will say NFM times 2 to the first power, which is NFM times 2. And that's exactly what we wanted. And every time we go through this loop, if you're unfamiliar with it, I encourage you to go through it. But every time we go through this loop, we'll build exactly what we have here. And then of course we need to change this so that it matches the output expression. So that's NFM times 2 to the I plus 1 power. Okay, I'm just checking that the parentheses match up, and I think they do. So after this, we have a network that's able to downsize our inputs to 4x4 feature maps. And now all that's left to do is to take those 4x4 feature maps and then turn them into a prediction. So the last thing that we have to add here is self.cnn plus equals. We're gonna take this convolutional layer. And now what we have to do is say, this will be 2 to the exponent minus 2. Because remember, that's how we got to 4x4 feature maps. And now our output is just going to turn it into a single prediction, so it's just 1. Then we have to change our stride to 1 and then our padding to 0. And because it's a prediction, we use a sigmoid activation function. So now that we've built our neural network, all that we need to do is put it in a sequential block. To do that, we say self.cnn equals nn.sequential, and we are going to unpack our network just by putting this asterisk here and unpack it into a sequential block. And all that does is put it in this format, basically. So it's as simple as that. And we could just copy the forward method that we used before because it's going to be the same exact thing. So here we have our complete neural network, and all that's left to do is to test it on different image samples just to make sure it does what we expected it to do. So now we're going to do the following. I'm going to create a new code block here, and this will test